Well, hello, everyone. Thank you for taking some time today to attend this webinar on filter cleaning and testing, of course. And today I'm very pleased to have Patrick Hill from Mott Corporation join me, as Mott is very active in the refining industry. So, Pat?
Yeah, good morning, everyone. Thank you, Susie, for having me. Happy to be here as a guest participant. And my role in this presentation is really to explain how the manufacturer interacts with the end user and the cleaning technology provider as part of the overall process.
Okay. All right. And as we think about refineries and fuel needs and that sort of thing, as we look at the global economy, it is so important that as you are producing your product, that you be competitive as you work toward the conversions of heavy and non-standard feedstock. Those are the difficult applications. And you want, of course, to push toward methods that produce quality products with a minimal loss. And that may be where filtration comes in. Filtration can add very important things to your process in terms of removal of various contaminants, whether they be hard solids, catalyst fines, or other types of materials that may come in with the feedstock. But
Susie, excuse me.
Sorry?
Share your screen. They're still looking at
we're not sharing. Oh, I'm sorry. Okay. Okay, are we seeing it now?
Perfect, thank you.
Okay, thank you. It was up. I didn't realize it had not been taken back or transferred back. So as I said, in this global economy, taking in the various feedstocks at the refinery, it is important that you make good product. And one way to do that, of course, is with filtration. But as you start looking at filtration, it is important to understand what it is you're trying to remove and how the filter should be designed and put into the process. And that will also mean considering what is going to happen when those filters start to become plugged and you have to remove them. Your decision then will, of course, be, do I clean or do I buy new? And so to help you answer that question, I know there will always be new purchases, but there are places where cleaning can be a consideration. And those are the kinds of things that we'll be discussing today. Now, as we discuss that, there are definite challenges. There are challenges for you as the refiner, but there's also challenges for us as the cleaner and the manufacturer. And some of those challenges will relate to media and metallurgy, the filter design and configuration, and also the contaminants that are embedding within the media and how they're loading. And so first of all, let's talk about some of the challenges of media and metallurgy. Well, media will definitely have an impact on the cleaning process that is used to remove the contaminants. Whether you're looking at some type of multi-layer wire mesh, sintered fiber, or various combinations of the various media, or if you're just looking at a porous metal media. So whenever we are looking at those types of things, we must consider not only the chemistry, but the mechanical delivery of the chemicals and how we're able to clean the filter. So one of the first questions to be asked is, well, tell me a little bit about your media. What are you using? And then, of course, the metallurgy, very important. In most applications in refining, for example, and we'll talk more about this a little later, high temperature oxidation processes are required. And then, of course, some various chemistries. So it is important to understand the metallurgy so that we can understand the restrictions, the constraints of that media in terms of temperatures or chemistry. For example, we would not want to exceed certain temperature limitations for a 300 series stainless. And we would certainly not want to use nitric acid with iron aluminide. So those are very important things to consider. And those sorts of things would be information that we would go to the manufacturer for, because the refiner or the user may not know the answers to these questions. But those would be questions that Pat would be able, or whoever would be able to answer for us. So whenever we're looking at how we're going to go about cleaning, media and the metallurgy, of course, is very important. Then we're looking at the challenge of filters and the configuration. In some cases, the entire filter bundle will be pulled and sent out for cleaning. And that may require a situation like this, where the individual tubes must be removed from the tube sheet. In some cases, rare, but it is possible that filters can be cleaned in the tube sheet, but those would absolutely be on rare occasions, and the design would have to be important in that decision. And so it may be important that we would have to remove the tubes from the tube sheet, clean, test, and then install them back into the tube sheet. And then, of course, you may end up sending your filters out in tube form, where you keep your hardware and you remove the tubes from your bundle. And so it is important for cleaning in terms of how do we rack, whether it's assembled or whether it is individual form. What type of connectors do we need for our flushing systems? And do we need welders for disassembly or reassembly? Process equipment is also important. If it requires high temperature processes, do we have an oven large enough to support your filters? And of course, packaging and shipping methods on the return trip. Very important. We have had filters come in containers or boxes that were not very stable, which could result in damage along the way. So boxes and how filters are shipped are a very important part when you're considering cleaning filters. Another challenge, and this is a big one, what are the contaminants? And tell me a little bit about the loading. Are the contaminants organic in nature? Are they catalyst fines that maybe have embedded maybe the outermost angstroms of your filter media where your backflush is not being very effective? If they are organics, where are they? Are they blinding the outside, or are they embedded within the media? And what are those organics? Could they be asphaltenes? Well, I guess that's the big name for refiners, asphaltenes, especially if you're getting feedstock that may not be as good as you would like, or if maybe your process temperatures or whatever have moved around so that you start having precipitation of some of these materials. So that can be a big problem. Or do you have organics? Inorganics. Are these inorganics inert materials such as diatomaceous earth? Or are they some type of salt where we can use some type of chemistry to break them down? So all of these are questions. Filters, when you consider cleaning, these are the kinds of questions that must be answered in order to develop an effective cleaning process to remove those contaminants and return that filter to like new condition. So how does this show up in your process? How do you know when to remove a filter, replace it with either a new filter or send one out for cleaning? Well, I will have to say up front to all of the refiners out there that this is just an illustration, okay? I'm sure your pressure graphs look a little bit different from this, but this is just a very abbreviated illustration of what may be going on in your backflush system. And backflush or blowback systems are very important when it comes to, say, an FCC unit where you are creating a catalyst bed either on the outside of the filter cartridge or on the inside. And that catalyst bed serves a purpose, either in promoting or not promoting certain reactions within the stream, such as sulfur removal or whatever, or just building a filter cake of some sort. So the problem is sometimes these catalysts will begin to break down and begin to embed within the media. And like I said earlier, this embedding may just be on the outermost angstroms of the filter surface, but can cause terrific problems when you're trying to blow these things back, because they may get, if you're talking about a porous metal or either some type of wire mesh configuration, these inert particles may get caught somehow within the media because they can have irregular shapes. And your blowback may be totally ineffective in trying to remove them. But what will happen you will start seeing increase in pressure. Your blowback system may try to continuously blow these things back, increasing the frequency between blowbacks and never a return to your clean pressure drop. Now, other things can cause this as well. If you start precipitating out asphaltenes within the media, your system may not be able to remove this. And again, you see the same result. So there can be lots of reasons why you're not returning the clean pressure drop as you would like, and your increased frequency between blowbacks begins to occur. And we call that the blue curve. So we'll be referring to this blue curve. So I need for you to look at that blue curve and kind of see what it's doing here. This gray curve would be representative, like I say, representative of what a new filter performance might be. You have a predictable frequency or time between blowbacks. You have a predictable clean pressure drop back to what your original is, and life is wonderful. But then, of course, we have bad feedstock, process goes sideways, something happens, and then things start to decay, and you end up with something similar to the blue curve, where there's really not enough pressure drop there for you to leave this filter online, and conditions start to decay to the point that you have to replace this filter. Now, once you replace it, if you put a new filter on that Patrick has sent down, then you would expect this gray curve to appear again. If you send a filter out for cleaning, the goal of cleaning, of course, is to return that filter to as close to a like new condition as possible. And when I say like new condition, what I mean is we have a predictable blowback frequency, and the clean pressure drop is similar to what the initial pressure drop was. Now, in actuality, we would all like to say that we clean the filter 100%, everything is great. And sometimes that happens. But in other cases, maybe there are issues going on with the filter where you do not get 100% recovery of the media, but it is enough to get you back to a process on-stream time, on-stream life, to where it's something that you can live with. So we refer to the orange curve as a curve that could represent that of a clean filter. And this is a picture, or a picture of some porous metal media that is plugged. And you can see that if you start embedding material in the media, or even on the surface of the media, where your backflush is not being effective, that this is what may be going on within that media. So when I say it's a challenge and a benefit, it's a challenge if you have issues, and it's definitely a benefit if you can solve those. So what are the cleaning steps that we might be using? Well, there's really, the way we look at it, 3 parts to cleaning. One is gross contaminant removal. And many times this is the step that is done at the refinery. Maybe you have a lot of surface contamination, oils, the internal part of the filter. Maybe it's a filter where the upstream side is the inside of the filter, okay? And so everything flows to the inside of that tube, and maybe some things go wrong and you end up with a lot of contaminant packing within the inside of the tube. Or it could be something on the outside. So the refiner tries to blow back or wash out or remove a lot of these materials prior to sending it out for cleaning, because many of these things could be hazardous. Now, but when the filters do arrive for cleaning, there's still some gross contaminant removal that's done before you get into what we call the deep cleaning. When we go into deep cleaning, we're trying to target what is embedded within the media. So with that, we want to remove anything from the surface, anything from the inside, so that when you look at the filter, other than maybe some discoloration from heat from the process, the refining process, it looks clean. So gross contaminant removal is very important. So we move to the deep cleaning. Now, in the deep cleaning, it's all about what are we trying to remove and what type of media are we dealing with here? Is it a wire mesh? Is it a porous metal? Or is it some combination of various media types? So it is important to understand those things. If it is a process, or if it is a contaminant that is going to require a high temperature process. And when I say high temperature, what I'm typically meaning is oven processing, using an oven. It could be a convection oven, it could be a vacuum oven, various types of ovens that will deliver temperatures in whatever range I need, 800 degrees Fahrenheit or 430C or even higher than that. And I know there are some metallurgies that are used in the refinery where you're going to have very high temperatures, maybe above the 800 degree Fahrenheit or 430 degrees C mark. In that case, you will go to an alloy other than a 300 series stainless, because that could be damaging to the stainless. And so you would go to some other metallurgies. And those are the things the manufacturer could advise you on. But we have to take into consideration what are the temperature limitations of that media before we proceed with this step. And it is also important to remove as much excess or loose or gross contaminants, especially those that may burn, before you go to an oven, because you don't want any side exothermic reactions that could exceed temperature limitations of the metallurgy and then create issues with the metallurgy, such as loss of tensile strength. So those are considerations. Now, another consideration that is important are the chemical steps. And there's always an issue. If you look at the pictures over here, this is a picture of something grossly contaminated. And I think you can see here's the metal and everything is filled up. I doubt your back pulse or back blowback system would clean that out very well. But here is a picture of the similar media that is cleaned. And you can see the open pores. So it's very easy to see how catalyst fines, broken catalyst fines can actually get in and penetrate these pores and actually cause you issues, as well as asphaltenes or whatever else that may be there. So we need a chemical cleaning method, say for inorganic salts, maybe some sulfides. You've got some maybe plating out inside of these channels. And so the problem is going to be, you can't just put the tubes in a bath and assume that you're going to have chemical percolation through these tubes or through these channels to get to the contaminant. So then, of course, it is important to have some type of mechanical flushing system, not just to remove particulate, but to also provide the chemistry. You must get the chemistry to the contaminant if you're going to break that contaminant down. Now, breaking that contaminant down may be a physical solution of it, or it could be a chemical reaction where we react with something to put it in a soluble form. It's all about solubilizing the contaminants to get them out of the medium. Now, there are times that if you're, say, using diatomaceous earth or you have sand issues in your process, you're not going to dissolve that. If you do, you're going to dissolve your filter as well. So what you're going to need then is some type of physical method. Maybe you will employ ultrasonics to help break these things down or loosen them from this very tortuous media matrix here. But then you will also have to come back with some type of flushing, whether it is high volume flush or pressure. Sometimes you need volume, sometimes you need pressure. So some of those sorts of things, sometimes you of course need both. So it is important to understand the contamination and the media matrix to determine how you're going to do your deep clean. And it may result in a combination of all of those. Now, the final steps, of course, will be descaling and final flushing. Now, when I say descaling, I'm looking at any type of surface discoloration, which could be just heat, which is not an issue for anyone, really, but it could be some type of plated out or deposited scale with an organic tail or possibly inorganic that's been left behind from some of the deep cleaning. So we'll probably need to remove those things. So when you think of filter cleaning, these are the kinds of things that you need to consider. But the question is that you should ask, how do you know it's clean? How do you know it's clean? Well, the only way to know it's clean is by testing, okay? Now, I did not include weights in here because these filters are very, very large in most cases. And the ratio of the weight of any leftover contaminant that might be in these pores versus the weight of the filter is so small until, can you imagine the accuracy of that balance that I would have to use? Wow. So we're going to look at other ways of trying to determine whether or not we have left anything behind, or also is the filter of good integrity. Even though the filter's clean, if the filter integrity is not good, then you may not want to put that or reinstall that back into your line. So how do we do this? Integrity tests are nothing more than pressure tests that are designed to characterize the size of the pores relative to the pressure created across that filter when you test it. Now, this is a very simple diagram of testing. You have a filter and a wetting agent, usually isopropyl alcohol, because of low surface tension, easy to wet these pores, and a pressure gauge, and you're going to have an entry of air. And we're going to control the amount of air that we put in. We're going to know what that airflow rate is. And so we slowly pressurize this filter where the pores have been plugged with alcohol. At some point, the pressure will build on the inside and it will find the largest opening, and that air will push through that largest opening. It will be seen and recorded. That pressure is the bubble point. So the bubble point is the pressure required to force the first stream of air through the largest pore. Now, the manufacturer will provide pressure ratings so that you will know if this filter is good or bad. Whatever the micron rating is, there will be a definite pressure, which if the pressure is lower, let's say the pressure requirement is 45 inches of water column. So if the pressure is lower than that, maybe 30 inches of water column, then that pore is bigger than what it should be. Now, why is that a problem? Well, you increase your pore size, and what will those catalyst fines do? Well, they'll just start embedding within the media, because when you designed your filter, you designed it for a certain catalyst pore size distribution or particle size distribution. So you want to make sure those catalyst fines aren't going to embed. Another problem, it could pass contaminants that you don't want to pass through the media. So it is important that you understand the integrity of that filter. Well, maybe one open pore is not going to cause you a problem. I mean, if you have a filter that's 10 feet long, 2 or 3 inches in diameter, how much contaminant is going to go through one pore? Maybe you're interested in the overall health of that filter. And so with that, we run a wetted airflow test, where we're now charging the inside of this filter with maybe 10 or 20 times the amount of airflow as at the bubble point. And what we start to see is bubble patterns across the entire filter. And it will also create a pressure drop. It's really telling you how much pressure this filter can hold against a set airflow rate. And we always like for it to be higher than what the manufacturer recommends for the minimum bubble point. So those are two tests that we run to characterize or define for you the integrity of that filter. But very importantly would be the cleanliness test. Good integrity, I could have a great bubble point, but 50% of the pores are still plugged. Oh my, you put the filter back online and we're back to the blue curve again. Remember the blue curve? We're back to the blue curve. So everything that we did to clean the filter did not clean it out effectively. So how are we going to figure that out? Well, for that, we use a dry airflow test. Now, when you run a dry airflow test, you always compare it to that of a new filter. Because if we challenge a new filter with a very high airflow rate up into several CFMs as compared to liters per minute with a wetted airflow test, you understand the resistance that new filter can offer to that airflow. And so we record that. And that's why for any of you that I work with, I always ask, send me a new filter so I can understand what type of pressure I'm going to develop across that filter with my dry air that will be acceptable to you. And I take that number and then I compare it to the cleaned filters. And it's all about percent recovery. We want to recover as much of the open space of that filter as we can to bring it back to a like new condition. And so we call that percent recovery. We have some little formulas that we use where we take our DAP, which is dry air delta P test. We pressurize the filter, we test it, we get our numbers, and we have equations that we can put that in that actually quantifies the cleanliness of that filter. So why is that important? Well, as you will see here shortly, you don't want to put a filter back online that is not as clean as it can be. or at least we tell you the degree of cleanliness. And we like to recover at least 90% of the DAP values across that filter, okay? So we want to recover 90% of the pressure drop. If it's less than that, we're going to reclean. But there could be some issues where you have embedded materials that cannot be removed. And in that case, we at least know that we can tell you, hey, done best we can, but you're only at 50% recovery. May not want to use this filter.
Yeah, and I think when you look at where the manufacturer fits in here, the tests that Sue mentioned here are critical. Bubble point, wetted air flow, clean flow. These are the same tests that the manufacturer performs during fabrication of new elements. And why is that important? That means that when you're looking at a data set, you can easily compare back to new. So it's the same test with the same production range, the same set of acceptable values. What does that deliver to the refiner? With that set of data and with realized elements that are cleaned over and over again, you can track the performance of that element. With that and with some help from the manufacturer and the cleaning company, you can have a decent idea on predictive maintenance. It's inevitable with porous metal elements in particular that over time, those pores will open up, whether that's through the cleaning process, whether that's through operation, whether it's erosion or something else. Those pores will open up and you will fall outside of that production range eventually. And so understanding how long that takes, whether that's years or decades or some other value, is very important because then as a refiner, you can be planning when you truly need to purchase new elements instead of when you can clean, which is faster and more sustainable because you're not discarding those elements over and over again. So it's very important that these tests are performed back to the same standards, the same production ranges as the original manufactured equipment. You want to switch to the next slide?
Yeah, there we go.
Thank you. So let's talk about some case studies. Process upsets happen. I think all of us on the phone understand that. So process upsets happen, unexpected situations happen. Overcoming those challenges is really important. And so outlined on this slide are just a couple of case studies that we have seen from some refining customers and how we were able to solve them. So what does the problem look like? For each of you, it looks like short cycle times. It looks like increasing DP with each subsequent filtration cycle, and ultimately decreased filter life. What does that mean? It means, unfortunately, you have to shut down the filters more often than you'd like. You need to open up those filters. You need to change elements out, maybe because they were ineffectively cleaned, maybe because there was a process upset, maybe it's a little of both. How does that come across to the manufacturer? The first thing we need to understand is, has there been a change in the design basis? Susie mentioned earlier in the presentation, filter systems, especially FCC and rFCC filter systems, are designed for a relatively predictable end state, a relatively predictable catalyst size and particle size distribution. Did that change? That would be really step one. If it didn't change, maybe there's just embedded contaminants that weren't removed. And so let's take a look at that through some microscopy work, through some cleaning exercises. Those would sort of be the initial steps. And once we have an idea on what's happening, what's causing the process upset, this is where the cleaning company can step in and do their magic, which is how can we remove those contaminants and get us back to a good filter now that we understood the upset and can overcome the upset.
Correct. And on the projects that we were brought into because of the problems that Pat has described, we were able to apply some of the processes that we have previously talked about. But by doing that, in order to do that, we were able to get some information from the user and from Mott in the analysis of what the problems were. And with that, we were able to design processes. And for each of the projects that we worked on, the process resolution was a little bit different in each case because the contaminants and the situation was a little bit different in each case. But And doing what we did, we were able to improve the process. Now, of course, there were other things that may have been causing the issues that we had nothing to do with. But the one thing that we could do was to effectively clean the filter and then provide the user with the degree of cleanliness so that when they did reinstall the filter, they were confident in the ones that they were reinstalling, and that number one, the integrity was good, and number two, they understood how clean they were. They were either greater than 90% recovery or less. So they had a choice of whether they wanted to use them or not. So it was not installing filters blindly. So we were very pleased with the results in those situations. Well, let's see. Okay. Oh, there we go. All right. Sorry about that, a little issue. Okay.
All right. So why do we go through this effort of getting a deep understanding of fouling, what's causing it, what the process upsets are, and how can we remove it? For each of you on the phone, you all have the pressure. You need to make product. Product is sold for money. Everyone wants to make money and be happy. So what is the cost of a filter change out? I'll start by saying that the numbers I put up on this screen are fictitious. I made them up. Be completely off, but I'm sure each of you has a pretty accurate view for your particular refinery. And so you can simply take this basic equation and knowing the value of your product, the flow rate of your system, how fast you perform your work, you can get an accurate cost specific to your end site. At the basis, though, relatively simply, you're filtering product so that you can sell that product for money, right? And so that product has a value, and maybe that value is dollars per barrel. Your system produces a certain number of barrels per day, and any day that it's offline, you're not producing those number of barrels, or you may be sending unfiltered product that is less valuable to different parts of your process. And so to understand the cost of having your filter offline, you simply just need to know the value of your product, how much product you produce in a given unit of time, and how many units of time is your system offline because you are dealing with this process upset. With some fictitious numbers here, let's say it's $10 a barrel, 5,000 barrels a day, because that's easy math, and I can hopefully do that without a calculator. And let's just say that it takes you 2 days total to cool down, to maybe you need to do a steam out or a soak type of operation. You then need to uninstall the top of your filter vessel, remove elements, change elements, install the vessel again, and heat back up. So let's say it takes 2 days to do all that. With these fictitious numbers, you can see that a single filter element change out results in a product loss of about $100,000. Maybe it's more than that. Maybe your system produces much more than 5,000 barrels a day. I don't know. Maybe your filtered material is worth more than $10 a barrel. But at the end of the day, it's still a decent amount of money. And when you think that an FCC porous metal filter generally lasts about a decade with regular external cleanings, when you start projecting that out over a decade, it can be significant. And so if you currently change out your elements twice a year, and with either a better designed system or more robust cleaning, a combination of both of those, you're able to achieve a 2x lifetime. That's a savings of $1 million over the life of those filter elements. That's pretty substantial, of course. I think everyone would like to see something like that. Of course, if you're cleaning or if you're changing out elements more often, you're going to get a better rate of return, right? Anytime you can defer having to shut down the system, you're getting that savings. And really, it's a savings in terms of producing new product.
Very good. So what are the benefits? When we talk about everything we've discussed today, I think one of the biggest benefits to the user is the coordination and the collaboration of the three of us in trying to figure out what the problem is and how to solve the problem. We depend on the user to give us information. What are your requirements? What's your filter configuration? What kind of specifications do you have? What are your contaminants? We've discussed these. And then it's the cleaner's turn to come up with the optimum cleaning process based on their knowledge, the experience they've had with these sorts of things. And of course, the testing. You just cannot de-emphasize the testing for integrity and cleanliness.
And as a manufacturer, what we provide is a deep understanding of the physical components. What are they like? How big are the elements? How do you connect to the elements? What is the metallurgy, the micron rating? And what cleaning requirements or restrictions do we have with respect to that? And lastly, it's integrity criteria. So we want to be able to provide both the user and the cleaner limits to operate in. Do not exceed a oven baking temperature of 800 degrees Fahrenheit, as Susie mentioned earlier. Do not exceed a differential pressure of whatever that value happens to be for the given element configuration. It's really best when all three of these organizations contribute with the knowledge that they know to help solve an overall problem.
So benefits are good things. It's all about throughput, as Pat described. That's everything to the refiner. And so it's important that when you put a filter in, that you know how it's going to perform outside of external issues in your process that are not related to the filter. You certainly want to understand how clean that filter is. And as he mentioned earlier, if you go with filter cleaning, as long as you can before you have to replace, there's definitely a savings in terms of filter cleaning cost versus that of a new filter. And turnaround, generally filters can be turned around depends on the number of filters, the process used within about a 4-week period as compared to 16 plus. And I'm not sure, Pat, you would have to comment on that. But then again, if you pull a dirty filter and just replace them each time, now you are dealing with environmental concerns in terms of disposing of these things. So these are the things that are considered, that are the benefits, that are the good things associated with filter cleaning. Now, in closing, the benefits for the refiner result when the cleaning vendor and the filter manufacturer work together to resolve the challenges associated with filtration. And we've talked about a lot of these challenges, such as reducing the costs associated with changeouts of improperly cleaned filters, developing effective cleaning processes for the project that we're working on, and validating the integrity and the degree of cleanliness prior to installation. That is so important. And of course, reducing the environmental impact of disposal. And we're ready for questions. Feel free to contact us with any other questions that you may have. And thank you.
Sue, Patrick, thank you so much for that great presentation. We are going to switch over to Q&A now. We have our first question from Andrew. What applications is porous metal filtration typically seen, and why is porous metal required for those applications?
Yeah, so at a refinery, on a liquid filtration setting, FCC slurry oil is a pretty common application. rFCCU would also apply to that. There are some hydrotreating, hydrocracking applications where you would want to use porous metal or maybe a tight wire mesh if it was a wire mesh manufacturer. Why do you use porous metal? I'll stay specific to FCC. What you're trying to achieve there is barrier filtration of aluminosilica catalyst fines. Inevitably, there are other contaminants in that stream, although what those are vary wildly based on individual refineries, individual FCCs, all that kind of stuff. But you're trying to achieve barrier filtration. So you want to make sure that you're capturing those catalyst fines on the surface of the media and are able to move those catalyst fines to a part of the process in an efficient and repeatable way, such that the refinery can deal with that stream.
Okay, I do invite you all to post your questions in Slido, or you're welcome to take yourself off mute if you'd like to ask something directly to Sue or Patrick. Anything else that you would like to discuss? Sue, Patrick?
Happy to answer questions. I think, presentation is nice, but certainly would like some dialogue. So if there's anything that you folks have questions on over the last 30 minutes of Sue and I talking, please let us know. We're happy to answer.
Absolutely. If you have particular problems that may need some discussions, please get in touch with us.
We do have another question from Jeff. For my clients that are using the sintered metal filter systems that we provide, how is a cleaning program designed?
Jeff, that is a very good question. When we look at a new project coming in, there's certain questions I ask, similar to what we've talked about. You know, what's the size of the filter, the metallurgy, and very importantly, what is the contaminant? What is the problem that you're having? Is it, do you suspect asphaltene precipitation? Do you expect the catalysts are breaking down? Are you filtering from the inside to the outside? Once we know all of that, then we start determining whether or not it's going to be just an oven burnout with maybe some particular flushing or ultrasonics, or if we need chemistry. So a lot of questions would be asked before we are able to design that process. Does that help?
Okay, John asks, have you applied in vapor phase and in pyrolysis oil applications?
Yeah, so
char and tarry components in these systems.
I'll speak for Mott specifically, John, because that's where I am, and similar manufacturers may have done different stuff. But for Mott, yes, we have. I only mentioned liquid solid separation, but of course we have gas solid separation systems as well. In refineries, third and fourth stage separators are a pretty common application for that. Char and tarry components are a challenge, but they are a challenge that can be overcome. You need to have a scientific understanding of the level of contaminants. You know, tars are in nature very sticky. So if you can imagine trying to blow back a tarry substance off the surface of a media, that can be challenging. So maybe you need to employ another scenario. Maybe you need to backwash or backpulse more often. Maybe you need to introduce a soaking operation if we are talking about a liquid situation. Or maybe you need to adjust pressures or velocities of that backwash in order to account for what is a more difficult solid to remove. They are certainly challenging. It really comes back to understanding scientifically before designing the system and incorporating that challenge into the system design.
In terms of cleaning, it's not going to really make a difference as to whether you're in these sorts of applications, because the problem when we get the filter to clean is going to be the same as discussed with Jeff earlier, trying to understand what the problem is and determining whether or not a process can be designed to remove that material from the media matrix.
Okay, our next question is, which could be the cycle life of the filter for catalyst in flue gas?
Yeah, Raphael, great question. I have to give a sufficiently vague answer because every installation is different. What I can tell you in a flue gas operation, the primary degradation mechanism is likely going to be erosion from high velocity of the catalyst. A gas operation typically can operate significantly longer than a liquid operation before needing external cleaning, such as the nature of a back pulse versus a back wash. But generally speaking, you know, a year or more between external cleanings should be a reasonable target, and a total lifetime of about a decade should be a reasonable target if the system is properly designed and operated.
Okay, Eric asks, how many cleaning cycles can be applied to sintered porous metal filters?
That is a very good question, Eric. And I'll start my answer by talking about a project where the process itself, I can't really get into what that process was, but it was very degrading to the porous metal. In fact, components of the metallurgy, you might say, were being removed, which of course was just destroying tensile strength. And so in those cases, they would replace after one cleaning. Not because of the cleaning cycle, but because of the conditions of the process and the effects they had on the filters themselves. As Patrick noted earlier, anything that you do to a filter, of course, is going to affect it, and that also includes cleaning. As you clean porous metal filters over time, there will be an effect on the filter. Plus, they're being used and then they're being cleaned. And so the important thing there in terms of how do we know when to remove them is in the testing. And so I think to answer your question more specifically, it's going to depend on the particular application and what the filter sees online and then what it takes to clean it. But most importantly is to test it, to monitor it, to know when to remove it from service. And so I think that is a historical answer for a particular application that they figure out over time.
Yeah, completely correct. So in this question that Eric has, I think to answer it accurately, we would have to exclude chemistry-based degradation from the process. There are applications that are so severe that even the best metallurgy, whether that's Hastelloy or some other type of exotic, will still corrode over time. It's a byproduct of the aggressive nature of the process. In that case, the number of cleaning cycles is not really a good indicator, but what it will do, to Susie's point, is every time it's cleaned, you get a data point. And so you can trend from that data point. Now, in a highly corrosive process, there may not be a lot of data points.
No.
But that's the nature of the beast. In a process like an FCC slurry oil, for example, and you have a stainless steel filter element, there really isn't a corrosion-based degradation mechanism. And so that's where the testing and revalidation to manufacture OEM specs is really important, because you can get that multi-year trending of an individual serialized filter element, and you can see the behavior of that element over time. And with some help from the manufacturer, and of course with the hard work of the cleaning company, you can then predict when that element will have to be retired from service.
Okay, our next question is from Wayne Freeman. Can feedback of the filter be used as a diagnostic tool to indicate process problems upstream? Yes,
yes, it can, and it does. It happens all the time. It's what my group does almost every day. The filter can be a great diagnostic tool, especially when you have historical data from a good known operating point. For example, let's say that you had a process upset, or let's say maybe you had a different feed stream, a different crude oil or something like that. You're seeing the behavior of the filter that is meaningfully different than what you're used to. Let's say your cycle times are less than half of what they normally are. Your differential pressure rate of increase is 2 times higher than it normally is. That will originally start as a question of, is the filter working properly? From that, you can then back diagnose what's happening. Maybe instead of the vast majority of your solid contaminants being alumina silica catalyst fines, maybe you've introduced some tar or wax or asphaltene through something else in the process. Maybe you have a heat exchanger issue where the temperature is so low such that you have some precipitation problems. So short answer is yes, the data collected from a filter can be used as an excellent diagnostic tool when you are able to compare it to historically good operation.
Okay, next question is, what is the monetary savings of cleaning a filter versus buying a new filter?
Well, in terms of filter cleaning, relative to the purchase of a new filter, Pat would know what that number is. In terms of what is done in cleaning, it of course depends on the process. It depends on how many filters. It depends on the size of the filter. Various things go into that. But generally speaking, I would say, I don't know, Pat, maybe 30%.
Yeah.
Certainly, I would say less than 50%. Again, it just depends. I'm sure if you have a Hastelloy cartridge versus a 316 cartridge, there's a big difference in the amount of, in terms of what those cartridges would cost. So there's a lot of depends there.
Yeah, I agree with the general range. One thing I just want to highlight here, obviously filter manufacturers want to sell filters, but let's not lose sight of the sustainability aspect here. Our filters are designed to be reusable over and over again. That's the purpose. We hate to see filters thrown away when they could be cleaned and reused, because that doesn't make any sense for anybody. It's generating waste at the plant. It's not taking advantage of the robust nature of the element, and whether that's Mott as a manufacturer or anyone else, I think the sustainability component will help drive the need to clean multiple cycles.
Okay, from Wayne, can Carolina Filters provide baseline testing for elements prior to the first installation?
Wayne, that is an excellent question. In fact, baseline testing prior to the first installation is key in understanding the trends that filter, that you can expect from that filter over time. Without a baseline, you don't know what your target is in order to return the filter to like new condition. So we baseline test filters in many different applications, and we request that because that's really the only way we're going to have a measure of how clean the filter is. And as Pat said, it's all about the trending. Every data point is important in the trend of the life of that filter. And so if you don't know where you're starting, it's not always clear as to where you're going.
Yeah, for the manufacturer, baseline testing helps us a lot when it comes to troubleshooting with you, the end user, because it eliminates a variable. We know for a serialized element how it performed new. So compared to that actual data from new and the actual data from cleaned, we can draw a pretty tight conclusion. Without that, we can still get to a conclusion, but of course we're talking about porous metal elements, which are irregular. They're irregular shaped, sized pores in general. And so with that, inevitably, there is a manufacturing range. And so we operate in that range, but having serialized actual baseline data certainly makes troubleshooting and optimization much easier.
Okay, that was the last question that's been submitted. Does anyone else want to pop off mute and ask anything of Sue or Pat? Oh, Eric has one more question. How do you test and clean a full bundle?
That is a good question. We have cleaned full bundles, and again, it depends on the contaminant. In the bundles that we have cleaned, we were able to use chemistry to actually break down whatever the contaminant is. There may have been a burnout as well, but it was we were able to primarily use chemistry to remove the contaminant. And so cleaning the bundle is not a lot different from cleaning an individual filter. It's just how you set it up. So as long as the chemistry is good. Testing can be a challenge in terms of how you're going to test an assembled bundle for integrity and for cleanliness. For cleanliness, it's not an issue because dry air delta P testing on a bundle is as easy as testing an individual filter. The integrity is the challenge. For those kinds of tests, depending on the size of the bundle, we can actually submerge, rotate, take depth measurements to the filter, and do some calculations to take whatever numbers we have and convert those to what it would be if it were under a half inch or an inch of whatever. But there's also some other things that we did where we fully wetted the filter and monitored the pressure rise and the pressure rise as we pressurize the inside of that filter, and noted when the pressure changed so that we could know when that first large pore opened up. So there are ways of doing it. Again, it depends on the size of the bundle and being able to use chemistry to clean the filter. But it can be done, and we have done it.
Okay, Raphael asks, what would be the approximate filter diameter for a flue gas flow of 5,400 SM3 per hour?
It's a great question, Raphael. To size a gas filter, there are a couple other inputs needed. We'll certainly need to understand differential pressure limits, solids, contaminants, probably a couple other parameters. I would be more than happy to answer this question, but maybe if you could send me an email, we can exchange some dialogue, and I can give you a rough sizing from there.
Okay, Sue, Pat, do you have any closing comments?
Well, I appreciate all of those who attended today to listen to our discussion. And I appreciate Patrick being available to add his input to the presentation. And of course to RevCom for supporting this. If you have any questions for either one of us, please give us a call. Thank you.